All right, today we've got a fantastic digital detective story for you. It's all about a brand new type of quantum encryption, one that was really designed to be unbreakable. And we're going to talk about the incredibly clever trick a team of researchers used to crack it wide open. Not with some massive supercomputer, but basically with a pen and paper.
So, just imagine this for a second. You've got a quantum lockbox, right? A cryptographic vault so mind-bendingly complex that even other quantum computers can't just brute force their way in. But what if the key to unlocking the whole thing wasn't really hidden inside the vault at all? What if it was written, plain as day, into the vault's own blueprints? That's the wild idea we're going to unpack today.
So to really get how this lockbox works, we got to go back a step. We're in this really exciting time for quantum computing where it's not just about proving these machines can work anymore. Now it's about finding new practical things to do with them. And one of the coolest ideas is encryption, which leads us to something called peaked quantum circuits.
So what exactly is a PQC? Well, the idea is actually pretty clever. Imagine you've got this powerful quantum computer, and you need to check if it's running correctly. You could write a special program that's designed to spit out one single answer, and only that answer, over and over again, with super high probability. If the computer gives you that expected answer, that peak, then boom, you know it's calibrated and working just fine. It's basically a tune-up tool.
Okay, but here's where it gets really interesting. What if you take that exact same program, but you don't tell anyone what that special answer is supposed to be? All of a sudden, your simple verification tool becomes a cryptologic lockbox. The program is still going to favor one answer way more than any other, but now finding that hidden peak is an incredibly hard problem. That hidden answer becomes your secret key, and this whole concept is the foundation of a protocol they call Little Dimple.
All right, so how did they actually build this quantum vault? To have any hope of cracking it, we first need to understand the blueprint. So let's take a look at the architecture they used to hide that secret key.
The whole thing is built on a structure called a mirror circuit. The easiest way to think about it is like this. You perform a really complex set of quantum operations. Let's call them a series of dance moves, U. Then, right after, you immediately perform the exact inverse of those operations. You run the dance in reverse, which is called U-dagger. So what happens? You end up exactly where you started. On a perfect quantum computer, this circuit does a whole bunch of complicated stuff just to end up with a string of all zeros.
So how do you hide a key in something that just returns zero? This is the really slick part. Instead of just sticking the secret on at the end, the creators imprint it directly into the second half of the circuit, that mirror reflection part. They just slightly tweak the parameters of that inverse program based on the secret key. What this means is the secret isn't in one spot, it's smeared out. It's woven into the very fabric of the vault's design.
Now you might be thinking, well, can't you just compare the first half to the second half and spot the differences? The creators thought of that too. To stop anyone from doing exactly that, they added two clever layers of defense. These are the traps set to foil any would-be codebreaker.
First up, there's the dimple. This is a unique little chunk of code they stick right in the dead center, right at the point where the circuit reflects. It's like tying a big messy knot in the middle of a perfectly straight rope. Its only job is to break that perfect symmetry. Then they used a technique called angle sweeping. Imagine taking every single number in the program and just randomly nudging it up or down a tiny bit. This creates what you can think of as a statistical fog, making it almost impossible to see the original, clean relationships between the two halves.
And this fog is exactly why the first attempts to crack this thing just fizzled out. The logical guess was that if you looked at all the numbers in that second half, they'd group together. You'd see a nice, neat cluster for every secret bit that was a 0, and another cluster for every bit that was a 1. But in reality, that angle-sweeping fog just smears everything together. Instead of neat little groups, you just get one giant continuous cloud of data where absolutely nothing stands out.
So brute force is a no-go. Statistical analysis is a dead end. What do you do? Well, this is the turning point in our story. The researchers realized they had to stop trying to kick down the vault door. Instead, they decided to start carefully reading its blueprints, the actual source code file called a QASM file that tells the quantum computer what to do.
And there it was. Buried in thousands of lines of nearly random-looking code, they found this very strange, very non-random sequence. A specific gate between 2 qubits, a couple of very precise rotations, and then that exact same gate again on the same 2 qubits. This was a structural anomaly. It stuck out like a sore thumb. It was the dimple, that knot in the rope, and finding it gave them the exact center of the entire circuit.
And that was the light bulb moment. The dimple, the angle sweeping,
All those clever defenses, they only add noise and complexity. It's like putting the blueprint behind a distorted, foggy piece of glass. But they can't change the fundamental laws of algebra that connect the first half of the circuit to its inverse. The mirror is damaged, sure, but it's not shattered. The relationship is still there.
And this is where the heist truly begins. Armed with this new insight, the attackers could now design an elegant, almost surgical attack that didn't require a single quantum computer simulation. They were going to read the key's signature directly from the blueprint itself.
The plan was simple, but brilliant. A three-step attack. First, like we saw, they scanned the code to locate the dimple and find the exact center. Second, they used some math to calculate the effect of that dimple and just digitally subtract it, basically untying the knot and giving them a clean line of sight. And finally, with the path cleared, they can do a direct one-to-one comparison between each operation in the first half and its corresponding partner in the second half.
So what did they find when they compared them? This. This right here is the whole secret. When you compare a gate's angle, we'll call it theta, in the first half with its partner in the second half, a dead simple pattern pops out. If the secret bit encoded there is a 0, the angle in the second half is just the negative of the angle in the first half, a perfect mirror reflection. But, and this is the key, if the secret bit is a 1, that reflection gets flipped again, and the second angle becomes roughly equal to the first one. That simple change in sign is the secret signature.
Now, think back to that angle-sweeping fog for a second. This is why it failed as a defense. That statistical noise, yeah, it can change the exact numbers. An angle of, say, 1.2 might get nudged to 1.1. But what it can't do is change a positive number to a negative number. Without totally breaking the whole circuit, the sign of the angle stays the same. And that sign is the tiny, clear signal that just leaks right through all that fog.
And this just shows you how much of a game changer this new approach was. Trying to simulate the quantum computer to brute force the key is exponentially hard. I mean, it would take a ridiculous, impossible amount of time. But this blueprint analysis, this algebraic heist, it's computationally easy. It turns an impossible problem into something you could probably run on a laptop over a weekend.
So, what's the big picture here? What's the takeaway from this incredible story? Well, this whole heist teaches us some really important lessons about where real security comes from as we enter this new quantum age.
It really boils down to 3 big lessons. 1. True security comes from a robust, fundamentally sound design, not just from piling on layers of complex camouflage like the dimple and the angle sweeping. 2. If your blueprint is public and the code for this circuit was public, it can betray its own secrets. And 3, and this might be the most important one, a clever mathematical attack can often beat defenses that seem totally impenetrable to brute force. It's brains over brawn.
And that leaves us with a really big question to ponder. As we build the next generation of encryption for this quantum world, where should we be focusing our efforts? Is the path to real security found by creating systems that are more and more complex, more and more noisy? Or is it found by building systems that have a simple, elegant, and provably secure structure at their core? That's a question that cryptographers are going to be wrestling with for years to come.